All right, so welcome everyone. Thanks for joining today. Today it's our pleasure to have Yannick Herfray, who will tell us about Cartan geometry of null infinity. Please.
Okay, so thank you. So yes, thanks a lot to Mark and Etera for the invitation. So it's very good to speak for the group from Lyon. So yes, I want to talk about geometry of null infinity. So it's always something that I discussed a year ago, 2 years ago. Yeah, no, this is a project that started 2 years ago, and since then is much more mature, as you will see. And yeah, so this is very classical subject, and you one might even wonder, how can you add anything new to geometry of null infinity? And I try to convince you that you can, and that there is this very nice framework called Cartan geometry, which really brings some insights on the subject and clarifies, I think, many things. So one thing about the sound, sometimes I notice that my microphone is not as good as it should. So if there is any trouble, please tell me. And sometimes it's good that I just turn off and on, and then it's improved. So don't hesitate to interrupt or ask questions. And also don't hesitate to ask questions along, and we can discuss along. Okay, so first bit of motivation for this work. Yes. So in the last years, it's been understood that gravity-S matrix, there were development in gravity-S matrix. So BMS group was understood to be a group of symmetry of the S matrix, and more precisely in the sense that part identities in the S matrix can be understood as Weinberg soft theorems. And there was also resurgence of interest for gravity memory effects, understood as being transition between gravity vector. Motivation for this type of works were at least twofold for me. So one thing was that it was realized along this line that Hawking's initial derivation of information paradox implicitly it relied on uniqueness of gravity vector, which was reconsidered and understood as being wrong assumption from these considerations. So it urged people, meaning Hawking, period, Schrödinger, to rethink about this problem. Another line of research is this idea of trying to think of the gravity-S matrix in terms of data, in a holographic picture in terms of data either as correlators of a would-be celestial conformal field theory on the celestial sphere. So this is this program of celestial holography, or in a very, as we sort of try to emphasize in recent work, or you can also think of this as being some a program of thinking of correlators on null infinity. So it's so notion of flat holography from null infinity. So from this perspective, what's interesting for me is that many of these results, they rely on subtle geometrical features of asymptotic flat spacetimes, which are already there at classical level and have been there for a long time. But if you're interested in this idea that you can sort of, which was already back there, it's a long idea that comes from a long time ago that you might be interesting to think of gravity from the point of view of null infinity. So, for example, there was this program of Ashtekar, asymptotic quantization, etc., Then you should really be trying to understand all these classical features deep, which are very deep and important, in terms of a fully intrinsic picture as null infinity. And this intrinsic picture as null infinity, I will refer to it as Carrollian picture. And I will explain where this name comes from later on. So this is my motivation. Yes, of course, a bit of words before that. So of course, asymptotically flat spacetimes, they are very classical tools. They are essential tools for understanding of GR. They model gravitational radiation as seen in LIGO. There is a very long history. So going back to this very classical work, this is just some works that I really like, but of a very long list. And in particular, geometry of null infinity is a very classical subject. However, one thing I would like to emphasize and I'd like to discuss is that from this classical picture, the results, they are not as intrinsic to null infinity as Carrollian as one might hope for a subject. And also it's related to some sort of conceptual clarity, some sort of question that you might ask in this context. So I mean, most of these results, they are really thinking in terms of geometry from the spacetime and not from the intrinsic null infinity perspective. Ashtekar is a bit different, but I will discuss this along. Okay, so in particular, there are a few statements which are, I think, conceptually unclear that you'd like to have a very clear perspective on it. One of such is that gravity vacuum is not unique. So exactly, okay, very good. But what exactly is the moduli space that we're talking about? What is this moduli space of gravity vacuum? What is the geometry behind? This is what I'm trying to say. Another thing that you will hear people say is that gravitational radiation forces the appearance of the BMS group. So it's very good, but exactly why and how is this happening? I think this have to be very clear. This should be very, very clear and obvious geometrical statements. And last one, which I really like, is the Ashtekar remark in his last review from 2018. He has this, I think, inspiring but vague way of putting things, that radiative aspects of general relativity at null infinity, they are close to those of a non-abelian gauge series, which is very good, but we're in 21st century, with being close to, what exactly do you mean? How close, in which sense close, what exactly is going on here? So of course, all these things, they are technical level, they are understood. People, this is something that's been around for 60 years. So in terms of computation, everybody knows what they are talking about. But this type of answer, they are not particularly illuminating, for example, especially if you're thinking from this intrinsic Carrollian perspective. And one thing I'd like to advertise today is that if you're building up on results which have been developed by people in the conformal geometry literature, so Gopher and collaborators, also something known as local twistors, in particular asymptotic local twistors, which is classical stuff. Well, then you can shed a very intrinsic Carrollian picture on this aspect. And here will be sort of my main point that I try to fledge during the talk, is the following one thing. So you can think of radiative characteristic data at null infinity, so at the boundary. So gravitational data at null infinity, you can repackage this as being some sort of invariant geometrical object at null infinity, which I call strongly conformal Carrollian geometry. And I explain what this is. But the main point is not, is that this exists and that this is invariant, but the main point is that this thing is going to be equivalent one-to-one with a choice of connection at null infinity, an intrinsic connection. Meaning that these guys, this Cartan connection, it has a completely intrinsic meaning. And this is somehow the connection that Ashtekar was hinting at without really, but he could not really explain where it was. So, but it's there. There is a Cartan connection. It's a genuine object living at null infinity. It's intrinsic. And then gravitational radiation is very straightforward. It's just the curvature of this object in the simplest sense of curvature. Is just, this is a connection, you take the curvature of this object. And also I should say, Cartan connection, they are close to, but slightly different from usual gauge connection. And in this sense, it very clarifies in which sense null infinity is close to being gauge theory. Okay, and then gravity vacua, then this moduli space of gravity vacua is just the space of flat Cartan connection. So you have all of this, you take the one with zero curvature without gravitational radiations. This is not unique. There is moduli space of this. They are space of gravity vector. Okay. And what's more, as I think all good change of perspective on a subject should give you some new ideas, new generalization you can have. I want to argue that it can. That this type of using Cartan connection suggests many generalization, higher spin, super geometry, also other sorts of ideas, generalization to space-like infinity, for example. And also you can use this to construct intrinsic functional, and that's been done in this work, for example. Okay, so here's going to, yes.
So just maybe you're going to explain this, but just to make sure, by radiation here you really mean shearing radiation, right?
Okay.
Okay.
Explain this. Yeah. This is okay. If you want this, you can say that what I call radiative characteristic data is the asymptotic shear. Yes. So here's going to be the plan of the talk. So first thing I will discuss what this intrinsic geometry of null infinity, which is known as Carrollian geometry, and discuss some result in elementary results, basic, let's say, results in this perspective. But I take a view which is a bit. I will take the view of Cartan geometry, and you'll see that it's inspiring. Then I'll discuss geometry of null infinity itself. And then at the very, I want to stress that all of this discussion is going to be fully intrinsic. So thinking of geometry just from the point of view of null infinity. And at the end of the discussion, I will come back on all of this and discuss how it fits, how does this geometry fit as being the boundary of some space. So let's start with Carrollian manifold. So yes, it all goes back to work by Lévy-Leblond and it's been advertised most recently by Duval, Gibbons, Forbati, Zhang. So here is what people call Carrollian manifold. You'll see it's very reasonably straightforward type of geometry, you want so you want the following setup of things. So you want nowhere vanishing vector field, which I'm going to note n. And the integral lines of this vector field should form a, let's say, it's from a trivial bundle. So what this all means is just that your manifold Sky is R times another manifold sigma. So practically, what you do is as you use local coordinates, U is local coordinates along R, YA is our coordinates on sigmas, and your vector field, it generates this R direction. So it's just some du guy. Now you want something like a metric, but it's not a metric because it's going to be, so it's symmetric, but it's degenerate, but it has constant rank. So there is a one-dimensional kernel, which you're going to ask that this one-dimensional kernel is generated by your vector field. So practically in local coordinates, this is all that it means. It's like these YAs, they are coordinates and sigmas, and your metric is like this. And on top of it, I'm going to require that the metric is invariant along the vector field, meaning that your metric is not U dependent. And I should say that this part, I'm going to require this because at null infinity, this is always happening. Einstein's equation in the bulk forces this as being your induced geometry at null infinity satisfies this because of Einstein's equation in the bulk. But people in the Carrollian literature, they like to relax this because it depends what you care about. Okay. Okay, so in particular, what this means is that this metric is a metric on the base. On the quotients, on the sigma, there is a metric. This is interesting.
Oh, sorry, Yannick, but why do you say this? Einstein equations, they don't imply that the metric is time independent, right?
So here, they imply that. Well, I'll come back in a minute. So yeah, at this stage, this is just really Carrollian, but the boundary of null infinity is really conformal. Is really a conformal variant of that. So there is rescalings, which I'm going to discuss in a minute, because it's conformal boundary. So just like in ADS, the boundary is conformal. Here, the boundary should be some type of conformal Carrollian manifold, and then this will be modified, as Mark rightfully pointed out. But yeah, so I'm going to discuss this in a minute. But why do people introduce this in the first place? What was the motivation? Because they were not, Lévy Leblond, he was not interested by null infinity. The motivation was that it's this type of geometry, they mirror Galilean manifolds. In the following sense, it should start with a space-time geometry, which here the null cone encodes the causal structure of your space-time. In the Galilean limit, the null cone opens up, it degenerates, and then your space-time gets foliated by slices of absolute time. So now in Galilean limits, your space-time is foliated by leaves of space. While in the Carrollian limit, you take the other limit, the null cone, they collapse in themselves, they collapse into lines, and your space-time is now foliated by lines. And so this is this picture, and then in this limit, you get this Carrollian picture where your manifold is foliated by lines. So this was the original motivation. It all goes back to this work of Lévy Leblond. He was really interested in contraction of the Poincare group. And by contracting the Poincare group in the Galilean limit, of course, you get Galilean group, but there was another limit that he emphasized, discovered. There is this Carrollian limit where you get the Carroll group. And his motivation for calling it Carroll was this, which I will let you read. So the way I understand it is that all of the characters in the mad tea party, so the mad actor, the crazy rabbit, they are all completely crazy. They are following their own Carrollian lines. But you see, in Carrollian space-time, there is no way in which the lines are causally related, because there is unique notion. There is an absolute notion of space which are not causally related. So they are all crazy and they are acausally related. Okay. So of course, as Mark already pointed out, this is not really what is going on at null infinity. Null infinity is a conformal version of this geometry because, again, conformal boundary has to be conformal. So really, the geometry induced at null infinity is the following thing. So it's Carrollian geometry, but up to some equivalence classes, which is the following. Is that you are allowed to rescale the metric, and at the same time, you should rescale the vector field in this particular way. Yes, and so in particular, then all the rest is the same, but of course, then you cannot impose that the metric equals 0 because it will break this equivalence. So what this is imposing is that the d derivative of the metric is proportional to the metric itself. So practically, what this means is that at null infinity, the metric is all the U dependence has to be in some overall rescaling factors. So of course, what you can do is that you can use this gauge freedom, this bias gauge freedom, to get rid of this, but this is not going to get rid of the bias scaling on the base. So whatever you do, there is always a conformal invariance on your sigma, on your base matrix.
Yannick, I think your mic is acting up.
Is what?
Your microphone is behaving funny.
Oh, is it better? Otherwise, the only thing I should do is no. Okay, let me.
Yeah, let's go on maybe and we'll see.
But you have some buzz sound, like something like this?
A little bit, but now it just became a bit worse. But
okay, let me try to turn off and on. Sometimes it improves. Yeah, so does it improve the thing? Or?
Yeah, no, it's good, but we'll see.
Yeah, I don't know what's going on with this one. Okay. Okay, so this is, again, yeah, this is really what is going on at infinity. You should always keep in mind that you have this bi-rescaling acting, and really, in general, this should be bi-rescaling, which are U-dependent. Of course, you can fix it, but in principle, it's there. All your theory should be bi-invariant in this very general sense. And this is, again, this is nothing, this was advertised by Duval, Gibbons, and Ratti as being conformal Carrollian structure, but really it goes back. Error a long time ago already pointed out that this was the geometry of null infinity, and he called it universal structure. What's interesting about this is that by itself, this universal structure, it knows about the BMS group in the following sense, is that BMS group is the group of automorphisms, is the group of symmetries of this very simple conformal Carrollian geometry. In the following sense, it's a group of diffeomorphisms on scry, which is preserving the geometry in this obvious sense. You act with your diffeomorphism, and you act on your geometry, and you should get some guy which is in the same equivalence classes as your geometry. If you suppose that your base manifold is a conformal sphere, then you indeed get that this group of symmetry is the BMS group in the following sense. So you have conformal transformation on the base together with super translations, which are doing something along the R directions. And then, in this sense, you recover the BMS group in a fully intrinsic way at net infinity. From this perspective, BMS group is nothing very complicated. It's just a group of symmetry of this nice structure. Okay, so it's nice, but at this stage, a group of symmetry is infinite dimensional. So where is Lévy-Leblond-Carrol's group in this picture? And also a closely related question, where are gravitational radiation here? So in a nutshell, the answer is the following. So if you want to recover the finite dimensional Carrol's group from this infinite dimensional BMS group, you need something called strong Carrol structures, which I'm going to review. And if you want gravitational radiation, you need something else. You need something which Ashtekar called radiative structure at infinity. And interplay between those two geometries, they are interesting but subtle. And you'll see that using Cartan geometry really clarifies, and homogeneous space is really going to clarify what's the interplay. Okay, so let me discuss this notion of strongly Carrollian manifold. This is sort of the most obvious thing you can imagine. So we had this metric and vector field. Another thing you might want to add is a connection compatible with this. So compatible in which sense? Well, you want the vector field to be preserved, the metric to be preserved, and you want your connection to be torsion-free. So it's completely, however, so this is the thing that you would do in usual Riemannian geometry. In usual Riemannian geometry, you would get a unique connection by requiring that your connection is torsion-free and metric compatible. Here it's different, it's Carrollian, so it's not working. So you don't get a unique connection, rather what you get is a moduli space, a family of connections. And they are related as follows. If you have two connections which are compatible in this sense, then they are related in like this. So their difference must be controlled by some symmetric trace-free, not trace-free. Their difference is controlled by symmetric transfer, which is 0 in the vertical direction, in null direction, and therefore it's just really something like this. And it's really should, this is really it's starting to look like some your shear. If you're used to BMS coordinates, this is of course your shear. But one thing at this stage is that precisely this is symmetric but not trace-free, while the shear of BMS coordinates is trace-free symmetric, and we'll see that this is a crucial feature. That will be the difference with the radiative structure. I'll come back on this soon. So okay, this is the definition. So you might want to ask, okay, do you have any good example of this? Yeah, there are many nice examples. So it goes back to, again, Bacri-Lévy-Leblond, and has been nicely discussed in this work of Faril and collaborators. Here are nice examples. You have there are model spaces for the Carroll groups, for the Carroll geometries, the strong Carroll geometries. And these are Carroll, the so-called Carroll de Sitter spacetime, Carrollian spacetime, and Carroll ADS spacetime. They are obtained as being Carrollian contractions of your usual de Sitter, Minkowski, and ADS, and they are homogeneous spaces for the Carroll groups. And here is how it works. Here is what they look like. They are all fiber bundles. You see, there is this R trivial factor. They fibers over some simple homogeneous space, Riemannian homogeneous spaces. So Carroll de Sitter is a fiber over sphere. Carroll spacetime is a fiber over flat space, Euclidean space, and Carroll ADS is a line fiber over hyperbolic spaces. And you find this in the structure of the groups, because you see all these Carroll groups, they are semi-direct product. And really what's going on is that this part, which is they are isometric group for the spheres, isometric group for hyperbolic spaces, or isometric group for Euclidean spaces. And these Rn, they are Carrollian translations. They act on the fibers, really. Okay, so these are, if you want, the claim is from that you can. No, actually, I'm going to show again why this is the case. But yeah, these are examples of strongly Carrollian manifold in this sense. Just very nice example because they are homogeneous. But there is a bit more, because in a sense, these examples they are the fundamental example in the following sense is that there is a notion. So the idea of Cartan geometry is that is to start with homogeneous spaces and make an homogeneous spaces curved. I'm going to review this in a minute, but and what you can prove is that in fact, if you making these homogeneous spaces curved in the sense of Cartan geometry, then you're genuinely finding strongly Carrollian geometries, and that's in fact it's one-to-one. So in this sense, not only they are examples, but they are all there is. Making this example curved give you all strongly Carrollian geometries locally. Yeah, and in particular, you will see in particular if this Cartan geometry they are flat. This is some local differential geometry statement. Then you get your strongly Carrollian geometries really just is this homogeneous spaces. Okay, so now what I'm going to do is I'm going to spend some time proving this. Yeah, so by the way, this fact was discussed by Yele Hartong for the flat case in this paper, and I discussed the non-zero lambda case more recently. So what I'm going to do is so the idea is that later on I'm going to prove I'm going to discuss a conformal version of this statement, which would be the result for null infinity. But here this is straightforward enough that I can actually go through the proof so that you can follow at every step and see what's going on. And then for the conformal case, it's going to be technically more involved. So I won't do this. But at this level, I can go through all the details. So let's try to do this. So first thing is exactly what is Cartan geometry. So this is the following. So again, the deep idea is that the Cartan geometry is a curve is trying to make homogeneous spaces curved. So you always mean Cartan geometry model on something, model on some homogeneous spaces. And here is what you need. First of all, you have a manifold M. You need a manifold which is an H principal bundle. So H is the group by which you want to quotient. Okay. And then you want not only this, but you want a connection, which is going to be G valued, where G is the group of isometry of your model. Then these are just assumptions to mean exactly what it means, G valued Cartan connection. But I mean, practically what this is that it's a G valued Cartan connection with H gauge transformation because the principal bundle is H valued. And the main example to have in mind is the flat model, which is the following one. So you start with G mod H, which is the thing that you want to. So this is M, but of course G mod H, because it's a quotient, you have a projection from G to G mod H. But what this means is that the fibers of these projections, they are isomorphic to your group H. So this thing is an H principal bundle over G mod H. So this is for the first point. And then what is the connection? Well, the connection is that you have a group, so you can always consider the one form valued in G, which is the more Cartan form on G. And it turns out that then this connection defines the Cartan connection. So this is the deep fundamental model of Cartan geometry. And why is it a useful notion? Because of this theorem. So this is, of course, going back to Cartan. And here's the following theorem: is that you start with a Cartan geometry, which is something like this. And this is an infinitesimal version of this model. And when is this? When are those two locally isomorphic? So when is your manifold M actually just locally homogeneous spaces? Well, this is the case if and only if the curvature vanishes. The curvature is some local. So here it's really straightforward. It's curvature in the sense that you're used to of the curvature connection. So the curvature in this sense is the local differential geometric obstruction to identifying M, your manifold, with some homogeneous spaces that you like. So I think it's very interesting because this is local and differential geometric, but this is telling you that M, whenever this is true, you know that M has some symmetries because they are isomorphic, so G acts. So it's some local differential statement about symmetries of your manifold. Very good. Now let's construct this Cartan geometry for this strongly Carrollian geometry that is discussed. First thing we need to do is construct this H principal bundle. So what is H? The model was this. So the H is iso n minus 1. Where is this principal bundle? Well, it's pretty straightforward. This is going to be the bundle of Carrollian frames. So we are used to use frame in general relativity, but here, of course, the geometry is there is a preferred direction. There is this null vectors. What you should consider is Carrollian frame, where one of the part of this frame is precisely the null vectors. And then the other one should be orthonormal in this sense. Of course, it's not unique. There are many such frames, but altogether they form an iso n minus 1 principal bundle. And here's how it works. There is an iso n minus 1, which is just acting on these A's, it's just turning them. And also there is a translation part, which is shifting E by a bit of the null direction. So altogether, this forms an iso n minus 1 principal bundle. So this was for the first point. So in this case, the H principal bundle is just Carrollian frame. And really it's going to be useful to consider Carrollian coframe. So instead of using vector field, you use forms. And I'm going to write them as L and theta's. So L is such that N contracted with L is 1. By duality, they also form an iso n minus 1 principal bundle. So this is something that has been introduced typically in the literature by people from Paris as being. You can think of this as being an LS-band connection on the infinity, but I mean, this is another way of saying that you're choosing a frame, and working with a fixed frame really is closely related to something which is called GHP formalism, which goes back to the 70s. Where it's some formalism that has been developed by people to deal with null tetrads. And this is what this is. In some sense, this is a null tetrad at null infinity. Okay. So this was for the principal bundle. Now we come to the connection. So we have to here's the most general Carrollian valued connection you can imagine. You have to trust me that this is valued in the Carrollian algebra. And you see that there are different fields. So there are theta's and L. So these are all one forms. Of course, it's one form. And then there are omegas and thetas. There are 4 fields. And what you should ask yourself is, are these fields transforming under gauge transformation for my H principal bundle? So are these transforming, if you want, under change of frames? What you check is that indeed theta and L, I choose the name properly in the sense that these are coframes. They transform like this under iso n minus 1 gauge transformation. And this omega and C, by what they are, is that they are components for a connection on your Carrollian geometry. They transform in the way that they should. So here, what they are, you can think of omegas as being this component, for example, and C as being this component of the connection. And in such a way that, okay, now this Carrollian connection really defines both a coframe and a Carrollian connection. You see, the fact that it's 0 really has to do with the fact that it's compatible. This connection is killing the ends. Okay, so this is how you see that it's 1-to-1, but at this stage, there is still no torsion-free notion. So where is this hidden? So it's torsion-free is going to be some exact extra requirement that you impose on the curvature. And the way you think of it from the Cartan curvature is as follows. So you write down the curvature, it's a straightforward exercise. and you realize that asking that your Carrollian connection is torsion-free is in fact just some algebraic statement about the curvature you want. So in general, it should be Carroll valued, but if you require that it's not Carroll valued, is valued in this subgroup by which you quotient, then doing this is the same as requiring that the Carrollian connection is torsion-free. This is, this was this equivalent. So torsion-free Cartan geometries, they are one-to-one with this strongly Carrollian geometry. Then nice. What you get for free now is that you computed the curvature. The only two bits in the curvature are this part and this part. So these are the obstruction for vanishing of the curvature. So now by Cartan's theorem, there is nothing to compute. It's just Cartan's theorem being used that this object, they are the obstruction to having local identification with the homogeneous spaces. Therefore, they are the obstruction for having the Carroll group acting on your strongly Carrollian geometry. So if you want, this is a version of this is a Carrollian version of this theorem that when in Riemannian geometry, whenever the Riemannian curvature vanishes, we know that if curvature is 0, then it means that your manifold is just Euclidean space-time. This is a Carrollian version of this. Whenever this object vanishes, then your manifold is just these homogeneous spaces. Okay. Yes. So this was for non-conformal Carrollian things. Now I will shift to null infinity, but is there any question at this stage about the overall philosophy? No? Okay. So now let me come to null infinity itself. So what was going to be the difference? Well, the deep difference is that null infinity, there are different features. Null infinity should be conformal first, but there is more. So how does it relate to Ashtekar radiative structure? Well, so as I recalled, if you have compatible connections on Carrollian manifolds, they must differ by a symmetric tensor C. So what Ashtekar called radiative structure is not this. Is going to be an equivalence class of such connection. And here is how the equivalence class would work: that you're going to declare that two connections, two strong Carrollian geometries, they are equivalent if and only if they satisfy the following property, that their difference should be a pure trace. So in general, this C is just symmetric. If the difference is pure trace, then you say that you want to identify two such connection. But this means that now radiative structure is going the quotient, is the quotient of this C by this gauge transformation. So now indeed radiative structure is a trace-free symmetric trace-free tensor. And indeed, this is what you expect. This gives you this is the asymptotic shear is a trace-free symmetric tensor. So at least in terms of degrees of freedom, it matches. So very good. So this goes back to the edges. I think this was Ashtekar was really trying to construct a picture which is fully intrinsic. Today we'll say Carrollian. And with this, he could do many things. He could discuss gravity vacua, relationship to memory effects, start this is asymptotic quantization. So it's a very nice picture. And I always think of this as being great and very inspiring. But I think there are many things that I would like to point out. First of all, it's not very satisfactory geometrically. I mean, working with equivalence class of connection is a very complicated thing. For example, how do you compute the curvature of such thing? Of course, it's going to be, you already know that just by seeing the definition, you know that it's going to be complicated. You compute the curvature for one, then you, okay, so whatever you do is going to, yes, Simone, you want to ask some question?
Yeah, Simone.
Yes, I was wondering why the first.
No, we can't hear you anymore, Simone.
Simone, yeah, sorry.
Can you hear me now?
Yes.
Thanks. I was wondering why in the first line you put the equivalence class in the connection, but not also on H and N.
Exactly, very good. So that's one of the things about this perspective is that indeed, of course, connection should be compatible with the metric. But of course, if you're rescaling your metric, then you should transform the connection accordingly. So indeed, so that's why really this story of Ashtekar, in some sense, was really not conformal invariant, at least not manifestly, in the sense that what really would.
No, but what I meant is that the fact that you end up with this formula in the box, in which you define this equivalence class with the difference being given by the trace part only, comes because you want to associate this connection not to H and N, but to the equivalence classes of H and N.
No,
if you write it in this way, I don't see the logic.
No. Okay, no.
That's what I meant. That was my question.
No. Okay. Very good point. So this is a very important point. Let's discuss it. So no, this is another layer of problems. So of course, if you're looking for equivalence class of H and N, this is making things worse. But as one thing that I think really Ashtekar really pointed out while doing this construction is that so how do you, from the bulk, how do you obtain nabla? Well, you take the Levi-Civita connection of your bulk geometry, so the conformally, the unphysical metric, and you're trying to restrict it at the boundary. So of course, in order to do this, you need to choose one metric in the bulk, which is not unique because you can do rescalings. One thing you can try to do is fix the boundary rescalings by choosing this representative. So you do this, and very good. Let's say you like to do this. But doing this, of course, is not fixing, is only fixing, if you want, the zero jet of value rescaling. There is still some value rescaling that you can do at subleading order in R. And this value rescaling is going to change nabla. So
let's imagine we have fixed that too.
No, but
just for a second. Just for a second.
Then if you do
this, fix that too, we have a unique connection, right?
Okay, so then in this sense,
the freedom, the equivalence class of connection is always related to the fact that there's an equivalence class of metrics at B.
Okay, but
so that's why your formula looks a bit weird.
Yes, absolutely. But then it's a matter of, okay, from the point of view of the space-time, this is what you're saying. So from the point of view of the bulk space-time, this ambiguity is related to the value rescaling ambiguity in space-time. Now, here, what Ashtekar, and I think here I'm really trying to push is how do you think of this from the intrinsic perspective? Well, the way you think of this is that you have two ambiguities. One coming from this subleading order of while in the bulk, which is ambiguities in this connection. Another ambiguities, which is due to conformal rescaling of the metric itself. So, I mean, of course, it's equivalent. It's just a matter of whether you want to think from the intrinsic perspective or from the bulk perspective. It's rephrasing of this freedom. Yes? Is that...
Go on, thank you.
Okay. But so yeah, this stage already. So okay. So first of all, you need to work with the current class of connection. Another way of saying this from the bulk, if I'm following you, Simone, is that from the bulk, this is really working with conformal geometry in the bulk, which we know is a difficult task. I mean, anyway. So that's another way of phrasing the problem. And also, yeah, again, here it's even worse than this because again, really this is only as nice as this because we are fixing the representative of the Carrollian geometries. So if you do wide rescalings here, this is going to be even more complicated. And one other thing that I would like to stress is that at this point, the Poincare group, the relationship to the Poincare group is obscure. It's absolutely not manifest anywhere. Of course, it's hidden somewhere, but it's in there. And also, all of this is subjective of a much simpler picture. And in Ashtekar's words, you know, there is something like a non-abelian gauge theory working behind. And I want to advertise that all of these points, they are fixed by this Cartan geometry perspective, which is very fully intrinsic also. I mean, I'm trying to present the story in such a way that you could sort of derive it. You can derive it just from the infinity itself. So what's if it's Cartan geometry, what is the homogeneous spaces lurking behind? So here it is. You can think of null infinity as being this homogeneous quotient. So it's going to be a homogeneous spaces for the Poincare group. So if you're working in 4-dimensional bulk dimension, null infinity is 3-dimensional. This is 4-dimensional Poincare group. And of course, this is absolutely similar to the usual story in ADS, where the conformal group of the boundary, conformal group of the conformal sphere of the boundary, is also the isometric group of the bulk. So here, the isometric group of Minkowski space is also some sort of conformal Carrollian group acting at scribe. But what's interesting is to compare this, in fact, not with ADS, but with some other homogeneous spaces that we already saw, which is Carroll de Sitter, which has exactly the same topology. It's R times spheres. So how are those things different? So first thing is that, of course, Carroll de Sitter is not conformal, while null infinity is conformal. And you see it by the appearance of here, the conformal group of the sphere, while SON is isometric group of the sphere. So that's one first obvious discrepancy. But what if you're trying to fix this? Because what if, so this is a sphere, so you can always, suppose there is a nice constant scalar curvature metric that you like on the sphere, you choose it, and then you restrict it. So it's null infinity in bounding gauge, meaning you're choosing one nice representative for your metric. Then, of course, what it does is that it reduces conformal transformation to isometries, so now it looks the same, but it's still not quite the same. And this is because, and why? Well, now because there's only 3 n Carrollian translation, while on null infinity you have 1 more translation active. So these homogeneous spaces, they are still different. So I think it's an important point is that just working, just fixing, you already see at the level of homogeneous spaces that just fixing the scale, working in Bondi gauge does not bring you down to Carroll geometry. And what this means is that for the dimension to match, you need to quotient by an extra R symmetries, an extra abelian R factors. And this means that there is an extra abelian gauge symmetry R in your Bondi gauge. And this R, of course, is the same, is going to be in the end of the day. This extra R shift is the shift of your connection that I just discussed before.
So just to clarify, by Bondi gauge here, you mean that the null vector is divergence free, or you mean that they've also picked a round sphere method?
I mean both.
Okay. So you picked the round sphere method.
That's what I mean. Yes.
Okay.
So you're absolutely. Yeah. So I mean, in principle, everything is conformal, but you're just choosing one metric in this conformal class, which is the round sphere metric. And therefore, it's just you go from conformal group to isometric group. But doing this is not enough to allow you to think of null infinity as being Carroll de Sitter. That's the point here. Yeah, it has to do with this extra R symmetry, this abelian symmetry has to do with this equivalence class of connection. So here is how things are going. So there is one thing which I'm going to define for which is this, which I'm going to call strongly conformal Carrollian geometry, which I'm going to define soon. This thing is going to be one-to-one with a Cartan geometry modeled on these homogeneous spaces. And in general, there is a flatness condition, which gives you an isomorphism. Now, if you work in Bondi gauge, you're fixing this part of the equivalence classes. You ended up with Ashtekar radiative structure. So now this is fixed, but you don't get one connection. All you can get is an equivalence class of connection. And you see this because in the flatness condition, it makes you gives you an isomorphism to this homogeneous model. And there is an extra abelian symmetry as compared to the Carroll manifold. But now what you can do is do an extra gauge fixing. You choose one connection in these equivalence classes, and then you really end up into having a Carrollian geometry, and your flatness condition gives you Carrollian geometry. And I should say, for Simone, because that's an important point, from the point of view of the bulk, this amounts to choosing in a row. It amounts to fixing the various scalings of the bulk, order by order. This is choosing the various scaling of the bulk at order 0, and this is choosing the various scaling of the bulk at order 1. So doing this gauge fixing is, from the bulk perspective, amounts to doing the gauge fixing of your unphysical metric in the space-time. But this is an intrinsic.
Just to remind you, because I don't remember anymore, but in the Ashtekar language, is this the difference between the capital omega and small omega, or no?
Capital omega and small omega. Yes.
So the fact that even if you fix a conformal factor, you can still choose a new multiplicative factor as long as it's Lie-Dragged.
Absolutely. Yeah. So okay. So little omega, I think, is this rescaling, is the boundary rescaling. But big omega is rescaling of the full space-time. So big omega is something that little omega plus, and there is
no, it's multiplicative. So then it's not the same thing. No, it's just the fact that once you fixed your conformal compactification, you can still require it to modify it by a multiplicative factor as long as this multiplicative factor is Lie-Dragged. And this further freedom, you can fix it by picking up a definite round to sphere method.
Yes. But
so that is all gone. So if I understand correctly, your scheme here, because by Bondi gauge, you said that you have picked a round to sphere, then both of these freedoms are gone. So the remaining freedom you're claiming it's in the connection should be something else on top of that.
No. Okay. So here I'm not. The part which is new is the Cartan geometry interpretation. Okay. It's not in the local differential. No,
it's just that it's hard for me still to digest what is meant by this.
So here I mean, in terms of the local differential geometric object, I'm not claiming anything new. So this is just the usual story. And so just to be clear, so you have various scaling in the bulk, which I think, yeah. And so if you fix the boundary metric to be some round sphere metric, the freedom in the bulk become various scaling, which are the identity at the boundary. Yes. So this is like fixing this part of the freedom. Now, what I'm saying is that I'm not inventing this. This was already Ashtekar pointing this point, is that now, even though you have various scaling, which are the identity at the boundary, there is still, at subleading order, your various scaling are still acting. They are not acting on the metric, but they are acting on the connection. So the subleading while rescalings, they are the ones shifting this part.
What do you mean? Sorry.
Okay.
What do you mean exactly by the subleading while rescalings? Because usually while.
So yeah, very good. Okay, so we have this. So you're doing your BMS expansion. Let's say. So R goes to infinity is the boundary. Is it yes? So your while rescaling of the metric is going to be lambda. You go from your metric g mu nu to lambda square g mu nu. And in general, lambda can be any function of R. So lambda is going to be lambda 0 plus lambda 1 R minus 1. Okay, so there's just an expansion in your while parameter in the radial coordinates. So the 0th order part of this expansion is rescaling this object. Fixing this, of course, does not fix the full while rescaling. You just now any while rescaling is going to be lambda equal 1 plus R minus 1 times something. And this something is not acting here, but is acting on the connection. And now fixing this dependence, choosing the connection is like fixing this lambda minus 1, this lambda minus 1 dependence. And by the way, if you count, this is the same number because it's one function and there is one function here.
Yeah, no, I understood. I agree.
Okay. And I think what's interesting is that you already see this discrepancy at the level of homogeneous spaces. This is what I want to point to, is that from this is the bulk perspective, but that from Scry, from this Carrollian geometry, here's how it appears. This is related to the fact that, again, just there is one more translation acting at null infinity that there is on Carroll spacetime. So this is related to that from the intrinsic picture. Okay, so now you want to sort of make sense of this in an intrinsic way. So how do you? What is this strongly Carrollian geometry, conformal Carrollian geometry? So you need equivalence classes, and then you need something which cannot be a connection, which should be some sort of object which is covariant under by rescaling. And here is what I claim you can do: is you can define something which is going to be a differential operator. I'm going to write coordinate expression soon, which goes from densities to symmetric trace-free tensor on infinity. And here is how it looks like in coordinates. So it's second order linear differential operator. It should be valued into symmetric trace-free objects. So here is in coordinates du, dy's, and here are the explicit expression. So if you want, and here in these things, what matters is that you have three objects which are the CAB, which is trace-free symmetric tensor. The claim here is the following: is that this differential operator, if you act on it with various scalings, if you act on it with diffeomorphisms, if you want this object to be a genuine tensor, to be a genuine differential operator on Scry, then this is going to be the case if and only if this object C transforms just like the asymptotic shear from your spacetime. So even if you have never heard of null infinity before, you could find, you would find again the same object by considering this differential operator at null infinity. I want to stress that as opposed to the connection before, this is fully conformally invariant. There is, this differential operator is just covariant under BMS, fully covariant. Okay, another thing I should stress is that this is not me making up these things. This object is a straightforward generalization of something which is known as Mobius operator, which is a classical object in two-dimensional conformal geometry. This is something that Cartan introduced a few years ago, and this object is just a generalization of that. So I'm just not making up something from the thin air. But why is it useful? Again, the reason why it's useful is that really this is the tensorial object and the differential geometrical object, which is equivalent to a normal Cartan connection modeled on these homogeneous spaces. So in particular, what this is going to be telling you is that anytime these geometries they are flat, so there's going to be a notion of curvature that you can compute. then being flat will be the same as equivalence to, will give you an isomorphism of the manifold with these homogeneous spaces, which is just what Ashtekar was called gravity vector. So from this perspective, gravity vector, which are the same as identification of a manifold with the model, are the same as flat Cartan geometries modeled on this model space, and they are the same as flat differential operator defined like this. Yes, and here, let me. This is going to. I'm going to just finish for this part on this. So if you wanted to prove these things, there will be again there are two steps. First thing you need to prove is that there is some principal bundle for this group, which is always there. And this is the case. You can prove that anytime you have a conformal Carrollian geometry, there is some principal bundle, which is principal bundle for this group, which is always there. It's canonically defined. So it's as canonical as the bundle of Carrollian frames. It's not something that it's not like a gauge group that you're putting on top of your manifold. It's something that is intrinsic, like a tangent bundle. And the way you do this is that you use generalization of factors techniques. I don't want to go in this direction, but if you're interested, we can discuss. And then, what about the connection itself? What is the result of just going through this computation that I was doing? So here, by the way, what I call normal Cartan connection. So this normality is some equation that you're imposing on the curvature, which is generalization in the notion of being torsion free in this context. So it's just algebraic constraint on the curvature. So, and here's the end result. So you start with this Poincaré, with this Cartan connection, which is normal, and you find that it's not unique, just like in the Carrollian case. Rather, it's parameterized by the following thing. So either in dimension bigger or equal to 4, so these dark dimensions are boundary dimensions, you get some zero mode of the asymptotic shear. So the asymptotic shear is the evolution is constrained by the equation. So only the zero mode is free. For n equals 3, then it's genuinely equivalent to choosing a full function on null infinity on scry. So this is the asymptotic shear. This is the characteristic data of three-dimensional asymptotic spacetimes. And in n equal to, something interesting is happening, is that the computation degenerates. And what you find again is that the freedom becomes a freedom of a function m in a moment and a one form NA. And from the bulk perspective, they are understood as being mass and angular momentum. So in this sense, this picture, this Cartan geometry picture, unifies all dimension. In this sense, the shear in 3 dimensions and the mass and angular momentum aspect in 2 dimensions, they are really the same object. They are really just parameterizing a Cartan geometry for these things. So in this sense, this is some sort of unifying picture. Okay, and here these are technical things about exactly how you make this work, but I won't really have time to discuss this. So let me come now to the. So this was the intrinsic picture. So in which sense you can think of this non-infinity as being just a connection, just a Cartan connection for this group. So let's see how it fits with non-infinity as being the boundary of something. So again, and because I want to emphasize this Cartan geometry picture, how do you see null infinity as being a boundary at the level of homogeneous spaces? So here's what you should do. So first of all, you start with conformally compactified Minkowski space. Thought as an homogeneous spaces for the conformal group of Minkowski space. So SO42 is conformal group of Minkowski space, and you find that the conformally compactified Minkowski space is this manifold. It's a conformal manifold, which is homogeneous space for SO42. Now we want to see the conformal compactification. So we want to see Minkowski space in there. How do you see Minkowski space in this conformal compactification? And what you need to do is you make a choice. You fix a Poincaré subgroup inside your conformal group, and by doing this, you're breaking conformal invariance. So you break conformal invariance, and by doing this, now the Poincaré group acts on this. Is going to act on these homogeneous spaces. And what's going to happen is that it's going to decompose your manifold into 3 orbits. One of the orbits under a Poincaré group is going to be just Minkowski space. Another orbit is going to be null infinity, and then there is a last degenerate orbit, which is a time-like or spatial infinity, which are here in this picture, in this homogeneous picture. They are all identified into 1 point. So what's going on? Yes. Yes. So what I want to emphasize here is that this is orbit decomposition. You start with one group, conformal group. You choose a subgroup, the Poincare group, and it's decomposing your manifold. It's decomposing one homogeneous spaces into three others, which are by construction orbits for the Poincare group. So this is in this sense that you see that this homogeneous spaces, null infinity, as understood as an homogeneous spaces, is the conformal boundary of Minkowski space inside the conformal compactification. So yeah, and of course, this is exactly the same. This is the null picture from something that we are really used to, the fact that the boundary of ADS is the conformal boundary. They are both homogeneous spaces for the same guy. Again. It's just that, again, Poincare group here acts as isometry group. Here it acts as conformal Carrollian geometry transformation on the boundary. Okay, so what's I think beautiful that I would like to advertise is that there is a curved version of this story, which is very nice. So here is how it works. So you start. So there's going to be holonomy reduction of conformal Cartan geometry. So you start with your conformal Cartan geometry. So a Cartan geometry modeled on the conformal group. This is, in fact, this is something which, in this context, is known as local twistor connection. And so before, the trick was choose one Poincare group, and then do orbit decomposition. So how does this make sense in this curved picture? Well, choosing one subgroup which is distinguished in this curved picture is like choosing the holonomy, restricting the holonomy. So you start with a Cartan connection for this conformal model. You require that the holonomy is in fact the Poincare group. This is some differential geometrical condition, and here is what it does. It decomposes your manifold, your curved manifold. Decomposing your curved manifold into different orbits, so to speak. One is going to call M, and one is the boundary. And then what it does is that at the boundary, you get a Cartan geometry for your for the boundary model, and in the bulk, you get a Cartan geometry for Minkowski space. And here it's nothing. So in the bulk, there is nothing surprising. So, but this Poincare connection that you get in the bulk is just, in fact, the Maxwell-Montsouris connection that you're getting from this from the conformal one, from the local twistor connection. But at the boundary, you get a new Cartan geometry, which is this Cartan connection that I just discussed before. So you see, from this perspective, there is no surprise from this perspective why this is happening, why there is this boundary Cartan geometry. I should say that this result is something which follows from very general theorems of Cartan geometry. It's known as orbit decomposition of Cartan geometry. But of course, anytime you have some big result like this, so it's like, this is very, very abstract theorem. Anytime you have such theorems, you want to see how it works in very concrete situations. And what I claim, what I proved, is that if you do this in this context for this particular group, what you find out is that holonomy reduction is really the same as having asymptotically flat spacetimes. So I mean, this discussion in the relationship with this thing that I discussed in this paper, and I'm using techniques which are almost classical by now in practice geometry. Okay, so here is the end of the story. So what this is saying is that anytime you have an asymptotically flat spacetimes, in the bulk, you have this Maxwell-Montsouris connection. At the boundary, you automatically get, by this result or by the result, yes, by this result, what you get at the boundary is a full Cartan geometry model on this model. What's more, and what is the very nice feature, is that in fact, what the curvature, what you understand from the intrinsic perspective as being the curvature of the Cartan geometry, from the bulk perspective, this curvature is just computing some bits of the vial at the boundary. From the vial of the bulk. So what you're computing as being an intrinsic curvature is, from the bulk perspective, is just computing this Newman-Penrose coefficient. And so in this sense, in this very precise sense, you can think of gravitational radiation, meaning this precise vial coefficient. And in this sense, this is curvature of the induced geometry, and therefore, by Cartan's theorem, this is just the obstruction to having a preferred gravity vacua, in the sense of having a preferred identification of your manifold with the homogeneous spaces. So this is in this very precise mathematical sense that gravitational radiation forces the appearance of the BMS group, because in general, there is no Poincare group gravitational radiation is the obstruction to having a preferred Poincare group at null infinity, acting at null infinity. Yes, and what I would again, so let me just be very clear about what is new here and what is not. So a local twistor connection is very classical thing going back to Penrose McCallum in the 70s. What is new here is its understanding as being some intrinsic geometry of the conformal Carrollian manifold, and also the Cartan geometry interpretation. Yeah. Okay, so let me conclude on what.
So can I ask you just, so is it the logic that somehow you sidestep the issue of working with conformal classes of connections because you get direct with this final result, right? In the end, you talk about some conformal invariant quantity like Weil.
Yes, exactly.
But at that point, you can make the connection again with the Ashtekar formalism, but your way of getting there avoids talking about equivalence classes of connections. Is that kind of the logic?
Yes, the logic from the Bell perspective, the logic is that all this, all these ideas, all this set of ideas is manifestly Weil invariant. Because I mean, they are, so you see, this was conformal connection. And everything in this construction you see is Weil invariant. So you never need to choose any gauge. It's just there. And you know that this thing is there just without any picking any coordinates. So yes, from this perspective, this is from the bulk perspective, this is what is going on.
And another question to clarify your last statement about the obstruction given by gravitational waves. But on the other hand, you would agree that if I'm in vacuum, but I do a super translation, then would you agree that I'm still in, so no gravitational radiation, news is zero, but I do some super translation, we usually would call this a different Minkowski, a different vacuum. With your red sentence here, would you agree in calling it a different vacuum? It seems like not. You would call it the same vacuum then.
No.
See, there's no news.
No. Okay, very good. No. So of course, what is going on is that if you're working without, so if there is no curvature in my language, no gravitational radiation, then you still have a moduli space of flat connections, and your BMS group acts on this. So this is why I wrote before, gravity vector is the same as the space of flat Cartan connection is the space. So this is the moduli space of gravity.
So there is an obstruction. So strictly speaking, there is an obstruction to having a preferred vacuum even without gravitational radiation, right? Because of this non-trivial action.
Wait, I'm saying something else. Here I'm saying now you fix one manifold that you like. You choose one nice, you fix one asymptotic flat spacetime. You're not allowed to change. You fix one. I'm saying here, the question is, can you, for this manifold that you choose, can you single out a gravity vector?
No, okay, this I agree, but the whole problem is that there's no way to get one in the first place. There's no way to get a preferred one in the first place. So that's why people talk about different value, right? There's no way to distinguish one asymptotic Minkowski from any other asymptotic Minkowski, right? Or are you saying that?
No, what I'm saying is that, you see, what I call gravity vector is you're trying is take your manifold, asymptotic flat spacetimes. There is some induced data at null infinity. Can you find a map from Scry to these homogeneous spaces so that when you pull back the geometry, it coincides with the geometry that you have? I'm saying so can you identify the boundary with the homogeneous spaces? Yes or no? If you can do this, this is the same as saying that there is an homogeneous, yes. And the obstruction for doing this is gravitational radiation. These are these Newman-Penrose coefficients, and this is also the curvature of the Cartan geometry.
Okay, thank you.
So I mean, just to be clear, this phenomenon is very specific. Let me just come here. This is where I wanted to come somehow. Yeah. So if you fix one spacetime, just working with one spacetime. Yes. So what is happening is that you know that there is a preferred Cartan connection at the boundary. Okay. So in all dimensions but d equal 4, this Cartan connection is going to be flat. So in all dimensions but d equal 4, you can think really of your boundary as being just these homogeneous spaces. But in d equal 4, so and then of course it's not saying that there is no asymptotic symmetries. You can still act with asymptotic symmetries. It's just going to change. It's going to act on your manifold. It takes a manifold to another one. It's going to change the gravity vector. But if you fix one manifold, there is one such identification which is possible at the boundary. In D equal 4, there is something else. There is the fact that in D equal 4, you can have gravitational radiation, you can have curvature for this connection, so you cannot even find one such isomorphism at the boundary for generic space. And you know, when I'm saying this is in the precise sense of being an obstruction. So I mean, what I want to say is that all that you were pointing out, Simone, is absolutely true, and just that this picture really clarifies how, for example, here D equal 4 is different from D equal 3. There are some parts which are similar. Asymptotic symmetries are there. They act on flat connections, but in D equal 4 you can have non-flat connections. So it's some other layer of things that can happen. Yes, and then you can think, you know, you can also rethink of the memory effect from this perspective, and it's essentially that been done by Ashtekar much before. So let me conclude on exactly what is what's the idea? What can you do with that? Again, there are things you can do with these sort of ideas which are very natural. You can construct invariant functionals. Just, for example, take the Chern-Simons action for this connection. It gives you something that you can study. This has been done in this paper. You can think of generalization. For example, to other spins. It's been started to be investigated in this work. But one thing that I did not touch about is another even more interesting invariants, which are charges. And of course, even though it's more or less known that they have Carrollian interpretations, there is a way of thinking of this as some intrinsic object. So the question is, can we reproduce these charges as being some in this conformal invariant framework? And actually the classical work of Penrose on quasi-local charges and work of Dugan-Mason, they suggest that this should be possible because you can define these charges in terms of the local twistor connection. But it's still not completely clear to me how you make this, you know, how do you think of this in an intrinsic way? And also perhaps more pressing question is, so the reason why people develop tractors, so this conformal invariant framework, is to proliferate invariants of conformal geometry. So can we here use this to proliferate new invariants, new charges, or some covariant things that will be invariants of physical asymptotic flat spacetime? And I think that's a very exciting question, but it's not completely clear to me at this stage whether or not this can be done. Okay, Matt, I will stop here. Thanks a lot for everything.
Thanks a lot, Yannick. All right, we have time for some questions. Yes, Fan, please.
Hi, can you hear me?
Yes.
Okay. Yeah, I just want to comment on Ashtekar's approach. So the thing is that Ashtekar defines these equivalence classes associated to those conformal gauge changes of the spacetime of the bulk that do not affect the degenerate metric or M. So in that sense, it's just a trick. You know, it's like saying, okay, I want to focus on the intrinsic structure of infinity, but I know that I have this conformal freedom, which is inherited from spacetime. So what I'm going to do is to say, okay, which conformal gauge changes do not affect my intrinsic structure? And those changes change the induced connection, okay? So that's how he defines the equivalence classes. And indeed, he does not fix the gauge. So the gauge, you have the whole divergence-free gauge freedom. I mean, you can do any conformal gauge transformation that that preserves that the second fundamental form of scribe is 0. So in that sense, yeah, you don't fix the gauge. And it seems to me that maybe you said that, or maybe I got confused.
Okay, so this was the discussion we had with Simone. Let me
yeah, I know it's that the discussion, but yeah, I didn't.
I agree with what you're saying, but let's try to fully agree. So yes, it's a trick, Okay, so all these things precisely, this is a trick to take into account byte invariance of the bulk. Okay, so as Simone pointed out, the whole problem here is really to be able to sort of have to carry with you all along treating byte invariance everywhere in your formalism, and you have to do it one way or another. So either you do it in a very, I would say, pedestrian way, as Ashtekar is doing it, but I should say already Ashtekar was trying to do things in a as coordinate-free way as possible, right? That was already what he was trying to do. And then you have to take into account that indeed you do not have unique connection, because doing this binary scaling that you are talking about is changing the connection, but it's worse than this, right? I mean, you can also change the boundary connection, and then it's even worse. You have to rescale the metric. What he's really doing is doing something which is allowed, but you have to keep in mind that this is what you're doing, is that you can, because you're working in 2 dimensions, there is a unique constant scalar curvature metric, diffeomorphism metric on the 2 sphere. So it chooses this. It chooses the round sphere metric on the 2 sphere. This is what I was saying. It's a choice of gauge from null infinity perspective. Why, you can do this. It makes sense, but it's a choice. You could work with another metric and it would be just as good. And in principle, I mean, I think you should really trace anytime you're doing any computation, what is depending on this and what is not.
But that's why they always check conformal invariance of their expressions.
Absolutely.
I think, as Fran just pointed out, there's no need to pick a gauge in their formalism. In fact, a priori, there's not even need to fix it divergence free, except that if you don't take it, so forget the round sphere, you don't even need to take it divergence free, even though then, of course, it becomes, I think it's not dragged anymore, so it's
you're absolutely right, but it's needed in the sense is how do you define what is at null infinity? This is crazy object, right? You won't say what is induced at null infinity is an occurrence class of metric. Right. Together with an occurrence class of connection. This is super bad. I mean, that's all I'm pointing out. Of course, you can do this, and you can say.
I think that's a strong statement.
Sorry, and I just wanted to point out that Ashtekar did not fix the gauge, nothing else. And
no, I'm not saying. Well, I mean, I'm not really saying this. No.
And just another comment, which indeed is something that confuses me, because this object, this symmetric trace-free object, this CAB, right? This C, which I think you call it the asymptotic shear, the shear. This is confusing to me because it is the shear. I think it's the shear only when you choose an origin in this space that Ashtekar defines, this space of connections or classes of equivalence of connections, and it coincides with the shear only if you choose an origin in this space. So in general, I want to say that for me, this object, this CAB, is more fundamental than the shear, in the same sense that if you take the new tensor, for instance, the new tensor does not coincide with the time derivative of the asymptotic shear in general, only on a specific choice of gauge, right? Yeah. So I think maybe it's just terminology, but for me, sometimes.
Okay, so let's clarify.
Like,
yeah. So very good. So yes. So indeed. So one thing about the new tensor. So what you want to call news is what Ashtekar called news, right? So difference between u derivative of shear minus whatever you call it, Carrollian tensor or something like this, right?
Well, the new tensor, it's this difference between this Cartan tensor and this mysterious tensor rho, which you can relate to the shear, to the derivative of the shear, but. This is a result from.
You shouldn't need to introduce a Carrollian tensor, right?
Yeah, it's exactly the rho tensor is the Carrollian tensor. Yeah.
So just one thing about this. So you see, why do you need this? Because precisely vanishing of news is not gauge invariant in the sense that if you do a binary scaling of the boundary, then this is not preserved. So you need to introduce this Carrollian tensor. Sorry,
the vanishing of the new tensor is a gauge invariant statement.
Okay. So
the instance is
okay,
switched by.
No. It means, sorry, Fran, it just
Ah.
means that you subtract the Geroch tensor because you want to get rid of the dependence of the new tensor on the conformal rescalings. It doesn't need to introduce this because it's not working. It's trick, sidesteps this process entirely, right, Yannick? You don't ever need to talk about the Geroch tensor.
Absolutely.
That's the advantage of your. But to answer Fran's question, wouldn't you say that you are in fact choosing an origin all the time? Is what you were saying also before. Now you have picked one preferred, whatever it is, and then your Cartan structure is always associated to this choice of origin. You can call it, or this preferred initial Minkowski. You wouldn't agree on that?
Well, I mean, okay. So in this sense, let's say like this. One thing you can say is that this Cartan geometry, they form an affine space, just like the shear form an affine space. So
I see. So you don't have a vector space. You really have just an affine space in your formulation.
No, absolutely. This here you don't have any.
We still have something to understand, I guess.
But yeah, there is something I wanted. There was some very good remark of you. Yeah, no, I forgot. Yes, I think actually I wanted to say precisely that indeed somehow the Cartan connection it encodes. Yeah, I mean, see. Okay, no, yeah, perhaps another thing I should say. So the Geroch tensor. This is a very deep thing. This is something which is global statement, right? It really knows about the topology of the manifold. All of what I'm saying is local.
Of the cut.
No, not
you mean R times S2?
Yeah,
R times S2.
If you were working on R times some torus, you would need some other thing, and I'm not even sure. Probably Geroch tensor would not be unique. No, it would not be. So, no, actually it would be, but it would be different. So this object is a very, very complicated beast, which has to do with the topology of your manifold. So in fact, one way of thinking of this tensor is that in general, there is no way. So you have an affine space of Cartan. Actually, you can phrase it like this. In general, you have an affine space of Cartan connection. There is no way of choosing an origin, a preferred one. But because if you know about the global topology of your manifold, you can choose one. And this is this Geroch tensor is essentially, well, I mean, it's even more simple. So I mean, okay. All I want to say here is that all this business that I'm discussing is really local statements. Geroch statement is something about the global topology. That's what I want to say. So yeah. So in particular, there is some such thing that you can call like curvature equals 0, which would imply news equals 0, but which is always conformal invariant. I don't know if I'm being clear. Okay, another way I should say that what you want to call the news is the same as this connection, and there is an invariant way of saying it's flat. Okay, perhaps, yeah.
Okay, thank you. Thank you for the talk and the answers.
Thank you.
And also, I mean, another thing that I would like to emphasize, because I think it's nice, and I think never been really discussed in this way, is this, is this picture of the fact that you can really think of that all of this is some orbit decomposition of Cartan geometry. It's very, in some sense, from this perspective, you could have, if you've never heard of asymptotically flat spacetimes, you could find again this very same definition, which is physically motivated by just, by just working through this. You're like, I really like this homogeneous species orbit decomposition. What if I take a conformal Cartan connection which has some holonomy reduction? Very natural question, but you would get is asymptotic flat spacetime. It's sort of very natural way to end up on this non-trivial definition of being asymptotically flat. And in this sense, this suggests generalization, because then you can wonder, okay, what about other orbit decomposition for other types of geometry, etc.
And I'm still wondering about what I asked in the beginning. Here the leading metric on the boundary is allowed to be time dependent, or?
So the conformal factor can be time dependent.
So I'm asking because, as you know, the psi4 is not only sourced by the shear, it's also sourced by time derivative of the boundary metric. So here, when you identify when you say gravitational radiation is the obstruction to finding a vacuum, and you diagnose this by having a non-zero psi4, but then it seems to me that there's not only the shear in here, you can also have a non-zero psi4 even if you have no shear. So do you see this somehow, or how do you handle this?
Yes, absolutely. So again, I mean, so you agree that the only time dependence that you can have in geometric is some overall scaling.
Yes.
Yes. So indeed, that's what, and I mean, this is why this formalism is useful for, is to think about this type of problem, because typically it's much more easier to indeed fix this Pilot scaling, work with metric which is not time dependent, go through something, and then there are many quantities that are much simpler, etc., etc. When you start not doing this, you want to work in a more general gauge where you don't fix this, then it gets more complicated. Actually, I don't have it in top of my mind, but of course you should have some time dependence eating somewhere. Even in the violin, etc. So what does it say from this perspective? Again, I mean, yeah, I think from this perspective, it's just that this formalism tells you how to compute things in an intrinsic way, which you know are going to be are going to be covariant under all of this. So yeah, I'm not sure if I'm answering your question. So your question again was, if I have psi4 equals 0, how do I know that this is the same as the homogeneous spaces? You see, the homogeneous spaces.
How do you distinguish between the two contributions that you can have in psi4? So the shear and the time dependency of the Weil factor. Maybe you don't have to. Maybe you don't.
Well, you don't have to. I think that's my philosophy from this perspective. You don't have to. They are both there.
Okay.
So more the way you distinguish, I mean, the classical answer in the literature would be, well, I can always choose the metric to be the round sphere metric, and you should do this. That would be the classical answer in the literature, but I don't think you have to. Then there are just different contributions for the same invariant object.
Okay. All right, very nice. Okay, so well, many people left, so thanks again, Yannick.
Thanks for the invitation.